Okay, so we're gonna do the introduction to the code base so that people can see about like what exactly is going on and how the project is structured. Um, so on the Scuffle project, there's basically two compartments. There is the video section of Scuffle, and then there is the platform section of Scuffle, which is the stream platform itself, and the video section is more so like the IVS implementation that we have. So on the platform implementation, there is the API, and then there's the website. Um, on this branch that I'm on right now, the API isn't operational on this branch, but on Leonard's branch, Leonard has improved this and changed this a bunch. So when we merge the two branches, then we'll have one branch with both the video and the API. So I'm right on the video branch right now. So yeah, the website is here, and the API uses a GraphQL schema. So this is the GraphQL schema on the API that we have. This is auto generated. And yeah, so let me go over it. So once you have this understanding that there's two components to Scuffle, it's the video section and then the platform section. Then it becomes a lot simpler to understand. So this is a mono repo. So we have at the top level directory, we have a workspace, and we have a bunch of crates here. So we obviously have all the video crates, and then we have the API crate for the platform, and then we have this crate called config, which is a design that Leonard and I kind of came to about a way to implement like config building into our API spec, and this allows us, or into our application. So this allows us to do like cargo, run video edge, and then we could do like -h. So sorry, I just need to build it. But once this builds, you'll see that we get like clap or CLI argument generated as well. So not just env and not just env and file system based arguments. You can also supply CLI arguments, which is something that's really nice. So no other config system does this, which is why we implemented our own. So yeah, you can see that it basically generates CLI arguments here, and you can toggle the logging mode, and you can provide everything via CLI, which is really nice. Yeah, so that's something that we did. That's why the config crate exists here. So we have a macro crate, and then we have a testing crate for that. And then we also have a common crate, which basically provides like a bunch of common utilities that we use a bunch in all of the applications, be it video or be it in the API or wherever. Yeah, so then we have this thing called a mask file or maskmd, which is basically a task runner. And we use this as our task runner. So we have a bunch of things. It's like make, except it's called mask. So it's like make, but it's not make. And essentially, you can kind of see here what we have. We have this build. We have clean, format, lint, audit, test, db, env, bootstrap, update, GraphQL, and count the like CLOC, which is basically counting the lines of code. So a lot of these are basically used by CI and not really needed to be used by you. An important one to be used is database migrate, prepare, reset, and up. So these basically let you set up the developer environment, because we have a developer environment that is located here under, devstack db, which basically has like our developer environment. So you have cockroach db, you have nats, you have mini.io, and then you have like a script to just create the bucket in mini.io. And with Mask, you can just type maskdb up, which will then basically run all of that, like those like database initializations and stuff, and set it up for you. And then you can do maskdb migrate, which will then perform the platform migrations on the database. So it will basically create the database for you and perform platform migrations. Currently, video doesn't exist yet, but we'll add that as well. And then you can also do mask creates, and then you can provide a name, which will essentially create a migration for you. And then you can add like the SQL migrations. But this is not really needed right now because pre 1.0 release, we're not too considerate about database migrations, which kind of just adding features directly onto the database. We're just changing these values directly as we need to. We don't really care too much about migrations because we haven't got a deployed application yet. So yeah, currently that's changing quite frequently, so we don't really use this command right now, but we will use it when we do post 1.0. Then there's something called bootstrap, which is a really nice command that we wrote, which basically installs everything that you might need to install. So it basically installs all the utilities that you would need, and it updates everything that you would need to do anything. We have the mask update command, which basically goes and updates cargo, Rust, and then npm or pnpm. We have the mask GQL command, which basically prepares or checks the GQL of the platform. So if you go mask GQL and then you do check, it basically validates that the GQL on the server from the GQL exported from platform API is the same GQL that is exported or that is stored in the schema file. However, this probably won't work now because I'm not on the branch with API installed. So that's why. But it'll validate the schema is correct. And that's this. So the video platform is what I'm going to be talking about now. And I'm going to kind of go over what each of these little crates do that we have here. So we have Edge, which is essentially going to be our file server. It's going to retrieve segments from like NATs, and it's going to do database queries to create sessions so that people can play back and watch, and other things like that. So this is what the video Edge is. Job is to basically sit between the player. So if you have to think about it, when a user would go to your website, the user would go to your website, it'll use our player, and then it will use video Edge, and then it will use either if it's a live stream, it'll use the NATS implementation. Otherwise, it'll also use DB. So like let's actually define this as like a room life. So if you're watching a room, what'll happen is, which means like a live stream, it'll be a user that uses the player, which goes to Edge, which then hits NATS and DB. And then this is basically populated by the transcoder, which is populated by ingest, which is populated by OBS. So it looks something like this. NATS and the database act as sort of like a middle or the communication bridge between Edge and the transcoder. So when somebody goes live on OBS, it will hit ingest, and then ingest will request a transcoder to be created, or if there's one existing, it'll request a transcoder to take the job, and the transcoder will take the job, and then the transcoder will start talking to NATS in the database to essentially basically store the state of the current stream and the video segments and the audio segments, so that a player that goes to Edge can then watch back the stream. And that's the entire kind of design there. If it is a recording, it's a bit different because there's no longer going to be this NATS or this. There's still going to be a database, but there's no longer going to be this side of the thing because it's no longer real time. So if we have this, now we just have DB like this. And then the player will request S3 like that. So that's essentially what happens currently. So there's no way currently to make it through Edge. Ideally, in like a perfect world, we'll have it like through Edge or through some other mechanism instead of being on S3. But currently, in order to make it cacheable and to make it in order to reduce the number of hops, we can't do it through Edge. So we do it directly through S3, and that'll sit in front of the CDN. But yeah, so that's currently how the life cycle looks for both rooms and recordings. And yeah, internal communication between these, like between transcoder and ingest, and is using gRPC. And then everything in NATS is like any sort of metadata and stuff in NATS is stored using protobuf, so that it's just universally decodable. And if you don't know what protobuf is, it's Google's better dumbed down version, I suppose, would be it's like JSON, but except it's without any of the curly braces, and it's not human readable. So that's kind of the difference. So we have this proto folder in the top directory, which contains some libraries that I've written and some procedural macros that I've written here to basically generate like the proto spec for us. So if you look at the proto, we have Scuffle, which is our proto. Our top folder, we have the platform proto. So this is currently for like events and stuff that get emitted through NATS, not public facing. And we have video, which has, like, for example, ingest here has some functions and some RPCs. So it has the watch, and then which takes in a streaming of watch stream and returns a stream of watch response. And this can be done through ingest, which is the API that ingest conforms to, and this is done with, the person that uses this API would be the transcoder. So the transcoder sends a watch request, and it gets watch responses. So it gets basically the keyframe, the data, whether it's the init segment, the audio, video, the timescale, everything like that comes from here, and then we can also get whether or not we're shutting down or whether or not we're ready to move forward. And ingest is the owner of this API, and the transcoder is the user of this API. But in theory, what you could technically do is you can make it so that many people can consume this API. Like we could extend this to be like, if we want to do something like captions or something like that, we could then have an ability to take the audio and maybe like only, instead of taking video, because you don't need video when you're doing captions. Maybe we can figure that out, but I'm not too sure about how that would work, but it's very extendable in that sense. Then we have this live manifest here, which basically just stores some state about the current stream. So in this case, it only stores the screenshot index because that's the only state that we have at a global level. Most of the state is actually stored by a live rendition manifest, which contains the state about what segments are currently ready or what segments are currently stored, whether or not we're completed, the current timescale, the total duration. Then we have some rendition info as well. And then we have other rendition info, so like other renditions, what their info is. And the info basically tells you about what the next segment index is, what the next part index is, what the next part segment index is, and what the last independent part index is. And these are integers that are basically used to handle playback. So they're used by the player to determine some things. So for example, in video, we can only play when there's a keyframe. So basically a keyframe is an independent part or independent segment. And knowing when the last one was makes it useful for us to switch between variants, because we can basically request when the next keyframe is, when there's a next keyframe for it to be used. And the same thing is for these ones here. We can do polling instead of just requesting frequently. So we can do some sort of polling mechanism, which makes it a little bit more efficient. And then we also store some of the data about the recording thumbnails. So essentially, we store about the data about the thumbnails that are stored here that are currently active as well. So I think technically we could probably move this to be stored inside the live manifest instead of being stored inside the rendition manifest. However, we actually need this on the edge side, so it saves an extra request by storing it here. We can look at kind of moving this away if we need to, but it's fine for now. And then we have some events. Yeah, so when we request a transcoder, this is the transcoder event. So we have the ID of the organization, the ID of the room, the ID of the connection, the ID of the request. And then we have the endpoint that is the callback. And then we have organization events. So like when the room goes live, when the room is ready, when the room disconnects. And these are some of the events that get emitted when there's organization events. And there's also a public API for the video stuff, which is gRPC as well. So we have like the events API where you can subscribe to events. Then we have the playback key pair API, which allows you to create tokens that can authenticate the playback. So you can have a token that is issued that you can have private streams. Then we have playback session APIs, which allows you to count the viewers, essentially. We have the recording config API, which allows you to set up recordings. We have the recording API, which allows you to handle how recordings are done. We have the room API, which allows you to reset stream keys, allows you to modify rooms, allows you to disconnect and delete rooms, stuff like that. Then we have the transcoding config API, which allows you to essentially set up how transcoding is handled. So you can choose, if it needs to have 1080p or 720p or what settings we can have there. And then we have just a whole bunch of types, which are the supporting types for these APIs. So you can see, like, for example, if we look just briefly at the modify request for room. So the modify request for room, this is a little bit dated, so we no longer use names, but it lets you basically modify a room here, and then it sets the modify mode. So you can either do an upsert, a create, or an update. So the default is upsert, which means when you do modify, and if you pass a room that doesn't exist, it will insert it if it doesn't exist, or update it if it does exist. You can change this by setting it to either create or update if you want to either update one or you want to create one instead of doing a upsert. So yeah, those are some of the things that are kind of nice. But yeah, so this API is going to change a little bit because we've changed how we structure things in the database, but that's actually what we're going to do a little bit later today. So that's kind of the protobuf spec. We also use something called Terraform to deploy things, but this is currently not updated with the latest stuff that's changing. So this will be changing soon, I guess. Once we finish up the video side, I'm going to be working on the Terraform deployments. But yeah, we use Terraform. What Terraform is it's basically some sort of representation of infrastructure as a kind of code, so that you can deploy it and you can add it to your source control, and you can then deploy and track changes to infrastructure in source control, which makes it really nice. Is the protobuf stuff in common going to be removed? You mean this file here? No. This is a test. So this is used by one of the testing things. So we need to just have it here so that we can write unit tests for this mechanism that we wrote here, which basically allows for, so unfortunately in Rust, there is no channel controlling mechanism for protobuf. So what we essentially have here is the ability to pass like a CNAME, and then it resolves a list of endpoints that can be there. And then it validates which endpoints there, and it load balances them by this load balancing mechanism. It like shares them equally. So it shares requests across the across all of these things. And there's nothing like this in Rust. So this is basically a port of the implementation that exists in like Java or like Python or like TypeScript, where they had this kind of load balancing system. Where it looks up the IP address and the A record and the AA record, and then it, it basically does this. And this is useful, especially in Kubernetes, when you have like a service, for example, that has a bunch, or a nameless service. Oh, sorry, not a nameless service. A headless service where it contains just the DNS name, and then it resolves to like 5 IPs or 6 IPs or 10 IPs, all the pod IPs. So essentially what you would have is you would have a headless service, and then it would be able to resolve the IPs that are underneath the headless service and then use the headless service directly, so that we can load balance the requests on gRPC. So this doesn't exist, so I wrote an implementation for it, and then I wrote unit tests for said implementation over here. And then it basically shares the requests between the servers evenly. Kind of evenly. As even as it can be. And that's why it's there. But yeah, so we can look a little bit closer at video, because there's a bunch of other stuff here. So when I spoke about the kind of the edge, the player, the ingest, and the transcoder, there's also a whole bunch of video libraries that we've written. So for example, we've written AAC library for decoding the headers of AAC, which is an audio codec. AMF0, which is a binary protocol that is used by RTMP. We have AV1, which is decoding the AV1 headers. Some IO utilities. Some exponential glob, which is used for RTMP. And also, I believe it's H.264 and 5, which use this as well. It's another binary encoding for numbers. We have FLV to decode RTMP. We have H.264 to decode H.264 and H.265 to decode H.265. Then we have MP4, which is a implementation of MP4 in Rust. Now, the questions might be coming in about why we used our own implementation of MP4 instead of the upstream implementation of MP4. So Rust librs has a MP4 crate called rsmp4, and I will show you why. Because the maintainer of this library has blatantly wrong values, and I made a ticket about this, and I said, hi, I was curious why pretty much all the boxes are private. It makes this library really annoying to use when writing a remuxer into MP4 or FMP4. I'm trying to take a raw FLV stream and generate a fragment MP4 segments. Basically, I want to construct the boxes and use this library to serialize them into binary. However, this library makes it impossible to do that due to the private modifiers in all the MP4 boxes. Wondering if this was intentional or just an oversight. Your library is great, by the way. I would love to use it. Hi. Yes, as intended. It's supposed to be a high-level API of the MP4 reader-writer. I understand that, but why? Why not provide high-level access and also provide low-level access? The cost of doing nothing, it simply adds features and doesn't retract from the library in any way. And he never responded. So this guy is definitely trolling. And also this guy's library is just wrong in certain places. There's a lot of these boxes. You can see that they have like only a couple of boxes here. Whereas our library, if we have a look at the boxes and the types, we have like many more boxes than they do. And we support many more types than they do. And also, I believe, Trex. I think maybe it's MVEX. There's like some boxes that are just blatantly wrong. So MVEX maybe. Yeah, so MVEX here has just a single Trex box, whereas part of the specification under MVEX It's actually a vector of Trex boxes as part of the specification. So there are a couple things that are a little bit different between their library and ours. For example, our library also contains a whole bunch of specification modifier or specification headers, which basically tell you exactly where in the specs this is found. So our library is just better, is TLDR. But yeah. And then we also have an RTMP library, which implements RTMP from scratch. And it's incredibly efficient and lightweight as well. So that was the big thing. We went away with for the RTMP implementation that we have here. It's super, super lightweight compared to other RTMP existing libraries that exist on librs. I can go through them. So this isn't really a library. Okay, there don't seem to be any, but this looks interesting. Stream SOT content to Twitch. Interesting. Okay, but the libraries that exist are on GitHub, which are basically XUI, I think, which is Lang Rust, maybe. RTMP Rust, Lang Rust. So there's Javelin, and then there's XIU. A pure RTMP implementation of a live streaming server. River, I haven't heard of that. So there's like Javelin, which is this one on GitLab. So Javelin exists. Javelin, there's a couple problems with Javelin. Is for some reason Javelin has support for HLS and these databases. It's not actually a library. It's not actually RTMP pure. It's more so a whole bunch of shit. And it was last updated 3 years ago, so it's kind of dead. Then we have XUI, which is actually actively maintained. However, their API for implementing RTMP is incredibly poor. So for example, here they use a bunch of asynchronous everywhere, whereas ours is completely synchronous. Our RTMP implementation is completely synchronous, except for the higher level driver. So what that looks like is here we have just synchronous APIs everywhere, and we write into memory and then copy the memory to the we copy the memory onto the connection, which is much better because we basically reuse a lot of buffers. So we reuse buffers instead of what's it called? Writing to the connection and then polling that it's complete. So instead of doing context switching, we actually just write into memory and then basically write it straight onto the connection afterwards, which makes it so much more efficient and also makes it so that we don't actually have to have async. So you can technically run this as synchronous. You would need to make a couple changes. So you would need to make a couple changes because the library itself is technically async. But how it would work is you would essentially, we would then do ready here. So over here, what it does is it just reads data and then parses chunks. And then the parsed chunks do process messages, which basically do the responding parts. But you could actually make this, because you see only the writes are done, but any of the protocol level stuff is actually all synchronous, which makes it really nice to use. Another thing about our RTMP implementation is it's very careful. There's a lot of anti DDoS or anti-DOS measures that are implemented into it, which means that there's like, it's very hard to basically create vulnerabilities here when it comes to the number of chunks and stuff, because we actually set hard limits here. Whereas like other RTMP libraries, they didn't really think about that stuff, so they didn't implement it. They implemented too close to spec, whereas what we do is we implement it with some saner limits compared to the spec. So technically, if you abuse the RTMP protocol, you can basically have like unrestricted memory. You can just write like infinitely many chunks and stuff into RTMP, and the RTMP protocol has to respect this. If you tried this with FMFPEG, you probably would get this as well. If you tried this with any sort of RTMP implementation like Nginx RTMP or anything like that, there's probably these like, if you abuse the RTMP protocol, you can create like arbitrary large memory consumption on the server. But so we make it very careful that the memory consumption of a single RTMP connection cannot exceed some certain limit to prevent those kind of things from happening. And then, yeah, then the last thing we have here is basically a transmuxer, which essentially allows you to take FLV tags and FLV headers, and it converts it into the corresponding MP4 headers. The MP4 that is constructed from here is not very good because it's designed to be a real-time RTMP converter, which essentially means that, a real-time FLV converter, which means that it will convert FLV into MP4 in real time. It has no context of the entire stream. It doesn't think about the entire stream, because technically if you knew about the entire stream, you could then remove a lot of the headers and stuff like that. But it's good enough to create a working MP4 from FLV, and then it's good enough to then take that and then put it into FMFPEG, and then FMFPEG does all the heavy lifting when it comes to the converting to different codecs. And then we also make a much better implementation of this under the transcoder side. So when we decode all of this stuff from the transcoder, from FMFPEG, so once we get the different variants and stuff out of FMFPEG, we then break it into different tracks, and then we break it into different we break it into different segments and stuff like that. So once we get all of that done, where would it be? It would be under track pauser. So once we get like all of that done, we create track samples, and then we can break this into parts and segments and stuff like that. And that's all done here. So that would make better optimized MP4s. And yeah, that's kind of where we are. So the video pipeline is really, really good. The only thing that's left to do on the video pipeline is to update the video API, to update the protobuf spec for video, and then update the video API itself. And that will then mean that we have a deployable IVS working solution. We would eventually also have to do some sort of implementation for adding the ability to like monitor about which connections are actually being used. So like to store that somewhere in the database, maybe about like for billing, because we would want to do a billing system based on usage, and based on hours consumed and watched. So we'd need to do that, and we'd need to have some sort of metric for that. But since this is going to be used by only us for now, it's not too big of a concern, since we're basically going to implement it directly into the video API, into the platform API. We don't really have to worry too much about billing, because we're not going to bill ourselves to use our own product, and we're going to self-host it. So we don't need to worry about that stuff. And yeah, so that is basically how the entire structure works. We have a CLA, which is a contribution agreement, and if you try and make a PR, it'll tell you to go sign the CLA, which basically is some legal things about how open source works. You can read through this. TLDR, technically when you make an open source project, if you don't sign a CLA, you own your contributions that you make to the project, and you can revoke the contributions at any time. So this is basically a protection against that, because if somebody commits something to the repository and we then add a whole bunch of commits after that, it shouldn't be allowed that they can revoke their commits. They shouldn't be allowed to take their commits away from the repository after some arbitrary amount of time. And the CLA prevents people from abusing their legal right to ownership of code. It basically means that you don't own the code that you commit, which is what you would expect. Because if you're committing it to the project, you're technically giving your code to the project. You're not keeping the ownership or the rights on the code. But yeah, so there's a bunch of things here. There's a code of conduct about what we stand to do, and there's also a contributing guide here. So if you have any questions, you can also refer to this, or you can just join the Discord, and then you could ask questions about that there. And yeah, so that's kind of how it works. Yeah, I hope you guys like it as well. So then there's also some design documents here as well that you can look at, and they might not be perfectly up to date. So if you have a question about something and you don't understand something else, you can ask us, and then we'd be happy to answer. This is kind of up to date, so this pretty much exists right now. But yeah, anyways, based